So in the last part of this workshop, we'll try to demonstrate a little bit the FlexTiles tool flow. We'll do this in a couple of steps. So we'll first describe use case application. So an application that we use to go through the flow and to show every step. So once we explain the application, we will actually go through this flow and show it running on the FlexTiles development platform. But we don't only have this platform, we also have the OVP simulator. So after we've shown it running on the platform, we'll go to the OVP simulator where we show the same application running again. And in the last section, everybody in the room can play with the Simplify framework themselves and actually trying out running an application on the FlexTiles platform. The nice thing here is you can do this without really knowing anything about programming. So I hope you stick around and try it actually out later on. So the demonstrator application. So we use an application, SUSAN, and SUSAN is an acronym for Smallest Univalue Segment Assimilating Nucleus. Well, basically it's an edge detect and corner detect application. So this application was originally developed at MIT to help doctors make sense out of MRI images. So this is maybe not the best example, but it looked quite funny. We have a head, and we're going to highlight all the edges in the image. So as I said, this one isn't very interesting because it's a very small part of the image. But if you zoom in here and you take a little bit part of the brain, this algorithm can actually help you highlight strange parts. This application is quite nice to use as a benchmarking, as a demonstrator application, because it's really a nice low-level image processing application. So if we take a look at the SUSAN application, you can see it exists out of several actors. So there's an input and an output, and there's several actors in between that each do their own task. So this is the original application as we got it. And well, one of the things we did, because we wanted to make it a little bit more interesting, we partially parallelized the application to use the manycore system more, and we added a pre-processing filter. So we added this pre-processing filter because we could use that to show dynamicity. So this filter we can turn off and turn on when needed. So for example, if we want to run the edge detect on a scene from a camera, so here you see a road, very dark road, and we want to, well, we want to enhance this a little bit because, well, we can't detect a lot of features in this image. So if we see, okay, we're in a dark environment, the visualization layer can reconfigure the application, or basically reconfigure that one part of the application, the pre-processing image, to enhance the image. So what it does is it stretches up the contrast of the image. And as you can see in this example, once enhanced, you actually can detect a lot more features in the image. So what we'll try to show later on is actually this application going through the tool flow and running on the FlexTiles platform. So if we take a little bit of a look at the size of this application. So as you can see, it's all the kernels, the actual computational code is very small. However, there's quite a lot of data being transferred between the actors. So while all the kernels are a couple of kilobytes, we can see in the bottom table that we actually have 64 tokens, so data elements of 2 kilobytes. We have 16 elements of 8 kilobytes. So it's mostly communication intensive. So now we have the application. We're going to go a bit to the actual tool flow. So as a high-level picture, it looks something like this. So on the top we have our several entry points to the tool flow. So if you're just starting off, you just have an idea about an application, you're not so familiar with FlexTiles platform, you use Simplify.de. This is a nice web-based GUI where you can simply, with a few clicks of your mouse, click together an application. And as said before, you don't really need to know what you want yet, you don't really need to program yet, you can just click it together very easily at a high level, and you can already start running it and see how it works. If you already have an application, but it needs to be refactored, or you want to analyze it more, we actually have Spear.de. Spear.de provides a more advanced entry point to the whole tool flow. And if you already have an application, a typical nested loop program that's already done basically, and you just want to map to the platform, you can also start at the SDFC level, which can convert this program to a format suitable for our tool flow. So what we'll try to show today is this part of the tool flow. So we start off with the Simplify framework, and then we show the hardware tool flow, a part of the software tool flow, and we show the output running both on the FPGA prototype platform and on the OVP simulation. What we won't show is actually synthesizing the platform. We would like to do this, but I assume you guys don't want to sit here 7 hours waiting for it to finish. So the top, so Simplify.de. So as I said before, Simplify.de is a web GUI to access the tool flow. So you get this nice web page where you can click together your architecture. So how does my platform look? So as you can see here, you have a couple of microblazes. This microblaze you can configure, and this way you can set up the whole platform. So we'll skip this part for now, and later on, before the hands-on, when you can actually play with it, we'll go into a little bit more depth about this. So we'll skip to the next step. So for now, let's skip to the application tool flow. So the application tool flow takes the application we've shown before. So what you see here, we have the description of the SUSE application, which is the graph. We have the source code of each of the actors. And the first thing we're going to do is actually analyze the resource usage of each actors. So we have a little bit idea of how big this virtual platform on which we're going to run it should be. And then once we've done this, we're going to ask the tools, okay, come up with a mapping. So come up with an idea of how the application should be mapped onto the actual resources. So once this is done, we generate some code. This code can then be compiled into one of these application bundles. So I will now show a very quick command line demonstration showing this process.
I will now give a quick demonstration of the software tool flow on the command line. So as you've seen in the previous diagram, we start off with a description of the application graph and a set of source code that actually implements the application. So if we do a listing, you can see here on the left the source code, and I opened up the application graph here on the right. So in the application description here on the right, you can see the SUSE application with its actors coming back. So you see the get image actor here. You see how all the actors are connected to each other. But more interestingly, here you see the actor properties. So here we see the actor property of the get image actor. And here we can specify for the what processor, what resources we require, and how you actually compile this actor. So we see the source code that implements this actor. We see here how the edges connect up to the parameters of the function implementing the actor. And above here we see the resource usage. So the instruction, data memory, and possibly the shared memory requirements. As you can see, currently the resource requirements aren't filled in yet, so they're all set to 0. So the first step of the tool flow that will be executed when I type make here. So the first step will compile all the actors and use static code analysis to figure out how much instruction and data memory is needed. So this is now complete. So let's open up the output of this step. We see the same graph again, and if we scroll down to the actor properties of getImage, we now see that the instruction memory uses around 2.8 kilobytes, the data memory needs around 7.2 kilobytes, and with this information, the second step, the mapping step, was able to map this application to the platform. So we get an initial mapping, and we can open up the output of this step, and if we check here, we see that for the Susan application on processor MB1, the put image actor was mapped. Now this mapping description is then used by the code generation tool to actually generate another build project that allows you to compile the application bundle. So if we switch to this output, you can see here subdirectories for each tiles and a make file that allows you to build the application bundle. So each tile generates its own subbundle, and then an overall application bundle is built specifying the whole platform. So if we take a look into this main bundle, we see 3 sections. So we have the section with the platform description, and we then have 3 sections for each of the tiles. And in these sections, the subbundle resides. So if we take a look into the subbundle, we see again the budget descriptors needed for this tile, and we see all the code needed to actually run this part of the application on a microblaze. If we then also take a quick look at the source code that gets generated, we see here the budget descriptors. So we see the budget descriptor for the tile that has 3 sub-resources, the processor, the DMA and the communication memory, and here we see the specification of the processor. If we take a look here, we see that the processor starts up with a bootloader. So this bootloader is also automatically generated and configures up the operating system, libpos, and adds the application and the task that are mapped to this tile. So the nice things about these application bundles is we can run them on the FPGA or on OVP without any recompilation required. So you can just load them at runtime, they will be loaded and executed.
So the same information put again on a slide. So the bundle actually contains all the loadable code for the GPP. If we have a part running on an eFPGA, it will contain the virtual bit stream. For the DSP, it will contain the code for the DSP. And maybe if you have some input data, you can also put this into the bundle, and this will be then loaded into the memory. But beside this code, it contains a description of the resource requirements. So this makes up your virtual platform. And we have reconfiguration data. So as before in the Susan example, if you want to switch between the 2 versions of this pre-processing filter, in this part you can describe which configurations to switch between and on which triggers to change. And again, this bundle, once compiled, you can load it without recompilation on both OVP platform and on the FPGA. And the compilation step here now has finished. And I hope I can quickly show it. So what we see here in the bundle is in the first part we have the .bds section. So this is the section that contains the platform descriptions, and we have for each of the tiles, the virtual processors, we have another sub-bundle. And then each sub-bundle again has a budget descriptor again, so describing in more details that part of the virtual execution platform, and it actually contains the code to execute. But, well, with just the application, we're not there yet. So what we want to do is actually now look at the hardware flow.